Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 4 Part A. Question 1 states, starting from the non-steady mass balance for a gravity drain tank with inlet flow Q, linearize the differential equation and derive an expression for the transfer function relating the height and flow into the tank. So to start out, we are going to draw our situation. So our system is a tank with some inlet with flow Q and an outlet with a flow of negative alpha, which is just some constant that's dependent on the size of the outlet hole, times h to the 1/2. Our tank has some liquid level to it with a height of h. So if we start evaluating your system with a mass balance, we end up with the rate of change of the height, and we're going to multiply that by area to keep our units consistent, is equal to our flow in, which is Q, minus our flow out, which is alpha times h to the 1/2. Now, our goal is to go ahead and use the Laplace transform on our equation, but we can't do that yet since we have this h to the 1/2 power. We need to actually go ahead and linearize the equation before we move on. And to do this, we are going to do a Taylor series expansion. So if we do that, we keep our first couple terms the same. And then for the expansion, we look at, or we evaluate at the initial steady state. And we're going to call, we're going to define some variables. At initial steady state, we're going to call our h bar, and our q bar. And then we're going to finish off the Taylor series expansion by taking the derivative at initial steady state. So that's plus 2 square root of h bar. So I don't know that those bars are super clear. There we go. And then multiplied by the deviation from the initial steady state, so that's h minus h bar. So now we have our linearized equation, and what we can do is define our deviation variables, and these are just the value minus the initial steady state. FQ. Same thing for our flow. And if we look at the derivatives for these, they're equal to the derivatives of our normal values. Okay. And now we can evaluate our equation at that initial steady state. And when we do that, on our left-hand side of the equation, we're just going to have 0. Since at steady state, you don't have any change. And then we're going to have our initial flow value multiplied by alpha. And this just stays h bar. Same here. Stays the same. But here we just have our initial minus our initial. Next, we are going to subtract our equation, and when our equation's at steady state, zero, this is flow at initial state. This. Okay. There we go. Now we can just start canceling some terms. So first of all, this here is just going to be 0 since h bar minus h bar is 0. These terms are the same, so we can get rid of those. And what we end up with is a h dt equal to q minus q bar minus alpha times 1 over 2 square root of h bar times h bar. And now we can see here that these are q prime and h prime. We put that together, we have a times dh dt equal to q prime minus alpha times 1 to h bar times h prime. And then if we want to put this in terms of our deviation variables, we can just replace this derivative, I guess I don't have to write out the whole thing, with h prime. Now we are ready to take the Laplace transforms. So the Laplace transform of dt is going to be h times s. The Laplace transform of h prime is big H, and the Laplace transform of q prime is equal to q. Now we're just going to substitute these in. So here we have a times hs minus our h prime evaluated at the initial state. Then we have q minus alpha q or 2 times the square root of h bar times h. Now this just goes to 0. And now what we want to do is isolate our output, which is h. So we can just bring this term over to this side. This is equal to q. Then factor out our h, as plus alpha divided by 2 square root of h bar, and then divide by that whole term, and that leaves us with as plus alpha over 2 times the square root of h bar over 1 times q. Now here, this here is our transfer function. And a more commonly known format for first order transfer function is k over tau tau s plus 1. And so we're going to rearrange these terms to put this in that format. And to do this, we are going to multiply by the reciprocal of alpha divided by 2 times the square root of h bar. And so we end up with 2a times the square root of h bar alpha times s plus 1 in the denominator. And then in the numerator, we just have 2 times the square root of h bar over alpha times q. And so what we end up with is this term down here being tau, this term right here being k, which leaves our transfer function being tau s plus 1 k times q. Now we are ready to move on to question 2. This states for a tank cross-sectional area of 2 meters squared and drainage flow of 0.5 times the square root of h meters cubed per second, where h is the liquid level in the tank, simulate the time response of the tank when the initial steady state flow rate of 0.5 meters cubed per second is increased to 0.55 meters cubed per second numerically using scipy.integrate.solve IVP. Compare the numerical results against the analytical result obtained by inverse Laplace transform of the corresponding expression from part A1. So this time I'm going to kind of work backwards and address the second part first. And here we have the analytical result that we got from the previous part. And based on this, we're going to do some inverse Laplace transforms. But first, I'm going to do the Laplace of q to rewrite this equation as h is equal to tau s plus 1 times k times q, which is the same as a over s. Now, a here is our magnitude of step. Now, if we take the inverse Laplace of this, what we end up with is h prime is equal to a times k times 1 minus e to the negative t over tau power. But what we really want here isn't h prime, we want h. So to change that, we just say that h is equal to h bar plus ak times 1 minus e to the negative t over tau power. Now, graphically, what we kind of expect to see with this is, here's our axes. Our x is going to be t, and our y is going to be h. What we'd expect to see is that we have our system at steady state, which is our straight line here, which would be at h bar, and at time 0 here, we're going to change the flow rate, and so we expect to see a step change, and we're going to see the height of the liquid in the tank increase. Moving over to Google Colab, we can go ahead and start on our simulation. First, we need to import all of our libraries, so import numpy as np from scipy.integrate import solve _IVP, and from plotly subplots import make underscore subplots. Perfect. Now we need to go ahead and put in some of our parameters and initial conditions. So first we have our area, our cross-sectional area of 2 meters squared. Then we have our alpha, 0.2. Our Q in initial was 0.5. And then we're going to increase our Q in to 0.55. H naught is equal to Q in naught divided by alpha squared. We're going to need our A value, our step change that we just talked about. So that's going to be Q in minus Q in naught. And then we are going to need the K value and the tau value from the transfer function. And those were K was equal to 2 times NP dot square root of H naught divided by alpha. And then tau was just K times A. Okay, now we can define our function. So we can define the right-hand side. Our independent variable is t, and our dependent variable is vector v. H is equal to v, and we're just going to put 0 because there's only we only want that initial value. And our differential equation, dH dt, is Q in minus alpha times P dot square root of H divided by A. Great. And then we just want to return our dH value. Great. Now we can do our solve IVP. As usual, we need to establish a Tn, so we're going to say 500. Res is equal to solve underscore IVP, our function right hand side. We're going to go from 0 to Tn. Our initial guess is H naught. Our method is redo. Say dense output equals true. Perfect. Now for plotting, we want to say that tplot is equal to np dot min space 0 to tend 100. H is equal to res dot sol tplot, and we just want the initial value because we only have one differential equation this time. Okay. Now for our plot, we could say that A is equal to underscore subplots, add scatter. The first one that we want to make is our exact line. So that's going to be, our x is going to be tplot, our y is going to be h, and then we're going to name it exact. And now we want to make another line, so add scatter. X again is going to be tplot, but y this time is going to be that equation that we just wrote out from the inverse Laplace. That here it was h naught plus a times k times 1 minus np exponent, and it is negative t plot divided by tau. And then I'm just gonna update the layout so that our width is 600, height is 500. Should spell everything right. Okay, well, something's wrong, and I forgot to name this. After reviewing my code, I found that my mistake was just that I forgot to put my parentheses around this term right here. So if I do that, now the graph looks like it should. And we can see that our linearized approximation is very similar to the exact value. And this just shows that this process works for when you make small localized changes, and you can get pretty accurate answers from that.